Hello and welcome to another NGen Math 7 lesson by eMath Instruction. My name is Kirk Weiler and today we're going to be doing Unit 8, Lesson 3 on more work with compound events. Now, as you recall, hopefully, from our last lesson we introduced the idea of a compound event, right? This is an event in probability that we're trying to find the probability that it happens, but that it's more complicated. There's more than one thing happening. Perhaps I'm flipping 2 coins or 3 coins or 4 coins. Maybe I'm spinning a pointer and flipping a coin or something like that. I'm doing multiple things, and so it makes it harder to keep track of all the equally likely outcomes that can occur in the sample space. Today what we're going to be doing is we're going to be looking at additional ways to keep track of those equally likely outcomes and calculate probabilities for compound events. So let's get right into it and discuss, right? Compound events can be tricky to think about because multiple things are happening. We will concentrate on what are called two-stage events, at least at the beginning, where just 2 simple events are combined to form a compound event. Then obviously if 3 things are combined, that would be a 3-stage event, 4 things, a 4-stage event, etc. So let's take a look at our first compound event, which will be 2 stages. Exercise number 1. A coin is flipped and a needle is spun on the 4-sectioned circle shown below. Letter A, create an organized list that shows all the possible outcomes in the sample space. And letter B, what is the probability that a head is thrown along with a multiple of 3? All right, awesome. Well, this is really what we did in the last lesson. So what I'd like you to do is pause the video now, try to create an organized list that shows all of the equally possible outcomes that could occur in this 2-stage event. And then, in letter B, try to find the probability that we got a head along with a multiple of 3. All right, as you can probably see, we are going to want to use our calculators just a little bit for today's lesson. If you've got one handy, break it out, and if you don't, that's okay too. Let's take a look at letter A. Now, right, an organized list. Well, keep in mind right here, in this particular simple event, we could get either a head or a tail. And in this simple event, we could get the number 3, the number 4, the number 6, or the number 9, right? So it's very, very easy to list out what can happen in each one of these simple events. Now, when we combine them, how do we make an organized list? Well, for me at least, I'm going to start by saying, well, what could happen if I tossed a head, right? Well, if I tossed a head, I could get a head and the number 3. I could get a head and the number 4, head and the number 6, and a head and the number 9. Those are all the things that could possibly happen if I toss a head on my coin. But of course, I could also toss a tail on my coin, and then I could get a 3. I could toss a tail and get a 4, toss a tail and get a 6, toss a tail and get a 9. And notice, right, I have a total of 8 equally likely outcomes. All right. And the reason that I have a total of 8 is because I have 2 here, and I have 4 here, and then I multiply and I'll get 8. It's a nice check, okay? It's a really good check. If you know how many outcomes there are for one simple event, how many outcomes there are for another simple event, then when you combine them in a compound event, you multiply those 2, and that'll tell you the total number. Now, I want to know the probability that I'm going to get a head thrown with a multiple of 3. Well, that means I don't look at any of these, right? Because those are all tails. And which ones were multiples of 3? Well, a head and a 3, a head and a 6, and a head and a 9, right? So I have 8 total outcomes. 3 of them fall into the event I care about, so my probability is 3/8. And again, there's absolutely nothing wrong if you like your probabilities better in terms of decimals, you know. So I could say, well, I've got 3/8. That would be in decimal form, 0.375. And in terms of percent, you could say 37.5%. Any of these would be acceptable ways to represent your probability, 3/8, 0.375, or 37.5%. Now again, this kind of illustrates a simple compound event. which is a little confusing. I've got 2 stages, flip a coin, 2 things that can happen. Spin the pointer, 4 things can happen. In this case, very easy for me to keep track of what can happen when I put the 2 events together, right? Or the 2 sort of like 2 stages together. I get these 8 total outcomes, simple enough to figure out how many of them fall into the category I care about. Now, we want to introduce ways to keep track of these things for even more complicated compound events. So let's take a look, and let me move my calculator a little bit out of the way. All right. One good way to organize the equally likely outcomes of a compound event is by the use of what we call a tree diagram. And these can be rather confusing for students, all right? So let's make sure that we really kind of lay one out together in the first problem. Exercise number 2. A coin is tossed 3 times in a row, and the result is noted each time. Create a tree diagram that shows the various outcomes, then change it into an organized list. So it'd be very difficult to do this with kind of a table like we did in the last lesson, because there's 3 things that are going on here. In a table, you typically can have an X and a Y, but there is no sort of 3rd dimension, or at least it would be hard to visualize. So what we're going to do is we're going to say this. Well, all right, let's say I flip coin 1, right? I could get a head or I could get a tail, right? That's it. Now, I think then about flipping coin 2. Well, if I got a head on coin 1, I could get a head or a tail on coin 2, right? But if I flipped a tail on coin 1, I could get a head or a tail on coin 2. So by this point, there's actually 4 outcomes: head, 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 tail, tail, head, or tail, tail, right? But we've got 3 coins, right? So for coin 3, right, well, if we had this one, we could still have a head and a tail. This one, we could have a head and a tail. This one, a head and a tail. And this one, a head and a tail. Sometimes teachers will then kind of connect these 2, but there's really no reason to. The reason that we might connect them is to make it look more like the branches of a tree. And again, you can really trace the things that are happening. Like for instance, if I go like this, head, 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 that means I got a head on coin 1, a head on coin 2, and a head on coin 3. On the other hand, this particular path, head, head, tail, means I got a head on coin 1, a head on coin 2, and a tail on coin 3. If I did a tail, right, a head and then a tail, that would mean a tail on coin 1, a head on coin 2, a tail on coin 3. So it just allows us to really be able to visualize all the different paths we could take in this compound event. Now, how do we use the tree diagram? Well, let's take a look at letter B first. How many total outcomes are there in the sample space? Actually, let me pause for a moment. I apologize. I didn't finish this. We were supposed to create a tree diagram, then change it into an organized list. So how do I change this into an organized list? Well, I have to be careful, okay? But let's start with a head on coin 1. I can have a head, and a head. So, right? Then I could have a head, and a tail. Right? Then I could have a head, a tail, and a head. Then I could have a head, a tail, and a tail. Now, by the way, I'm listing these, but it's okay if I started down here, right? It wouldn't matter. I just need to get them all kind of listed, an organized list. Then I could have a tail on the first one, a tail, a head, and a head. Right? Then I could have a tail, a head, and a tail. Then I could have a tail, and a head. And finally, a tail, and a tail. All right, and there's my organized list. That's everything that can happen. Everything that could possibly happen, right? Now, letter B is pretty easy. How many total outcomes are there in the sample space? Well, let's just list them. 1, 2, 3, 4, 5, 6, 7, 8. There's 8 of them. Now, let's get back to just for a moment talking about why are there 8? Well, right, on coin 1, there were 2 possibilities, head and tail. For coin 2, there were 2 possibilities, head and tail. And for coin 3, there are 2 possibilities, head, tail. Now remember, I'm not adding. I'm not doing 2 plus 2 plus 2, then there'd be only 6 total outcomes. No, I've got 2 times 2, which is 4, right? Times 2 gives me that 8, right? So, you know, if I flipped 5 different coins, right, and I wanted to know how many total outcomes there would be, I'd do 2 times 2 times 2 times 2 times 2, and I'd actually get 32 total outcomes. Here I've just got 8. And now we can finally answer a probability question, letter C. What is the probability of getting all the same side to show up on the 3 tosses? All the same side, meaning either that I've got 3 heads showing or 3 tails showing. Well, how many events show up into the category of all the same side? Well, this one up here, this one down here. So that looks like it's going to be 2 out of 8. So that's a good probability, 2/8. If you really wanted to, you could reduce it down to 1/4. That's a good probability. If you wanted to change it into a decimal, you could, 0.25 or 25%. And you can imagine, right? You can imagine tossing 3 coins and getting all heads and going, wow, can't believe they all turned out to be the same. Man, that's probably pretty unlikely. But in fact, it's actually 25%, right? There's a 25% chance that you could get all of the same thing showing if you toss 3 coins. And although that's not an overly high probability, right? It's 25%, it's less than half. It's still reasonable. You know, I could see that happening. Now, if I tossed 4 coins in a row and they all turned up to be heads or all turned to be tails, that would be even more rare. All right, so let's keep working with these tree diagrams. They're one of the major ways that we keep track of things with compound events. Let's take a look at exercise number 3. A person tosses a coin and rolls a standard 6-sided die. The person notes whether the coin lands on heads or tails and what number, 1 through 6, is rolled on the die. Letter A asks us to create a tree diagram to the right showing all possible outcomes in the sample space. All right, awesome. Now, a natural question, unlike in the last problem, would be, should I start with the coin or should I start with the die? And the answer is, it just doesn't matter. Your tree diagram will look a little bit different depending on which way you do it, but the answers to the probability questions will be the same. Now, I like the idea of starting with the coin, right? Because if I start with the coin, then the coin can turn out to be heads or tails. And I'll kind of join these things with a general branch like that, right? So that's my coin. Now, if I tossed a head on my coin, then of course, I could have a 1, a 2, a 3, a 4, a 5, or a 6 on the die, right? And if I tossed a tail, I could have a 1, a 2, a 3, a 4, a 5, and a 6 on the die, right? By the way, if you did it the other way, right, if you started with the die and then went to the coin, right, your tree diagram would look different, right? It would look more like this: 1, 2, 3, 4, 5, 6, and then off of each one of these, you'd have heads, tails, heads, tails, heads, tails, heads, tails, etc. Either one of these would be an acceptable tree diagram. Either one of them. And both of them, by the way, would tell you that there were 12 total outcomes, right? In this case, you know, you'd say, well, I've got 2 times 6, 12, or in this case, you'd have 6 times 2, 12. You can always tell in a tree diagram how many total outcomes there are by counting how many terminal branches there are, branches that just end. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, or 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. There's 12 total outcomes. which now allows us to start to answer probability questions. Let's take a look at letter B. Find the probability of flipping a tail and rolling a number less than 3. Well, we know the denominator is 12. Why don't you pause the video now and come up with the entire probability? All right, well, we know that the denominator is 12. Again, there are 12 total outcomes. The question is, how many of them fall into the category of having a tail and being less than 3? Well, I'm going to use this one over here. We've got to be on this branch, and the only ones then that are both a tail and less than 3 would be this outcome and this outcome. That's it. Right? So at the end of the day, my probability here is 2/12, or if you like 1/6, and its decimal version, etc. I'm just going to leave it at 2/12 and 1/6 for now. It's not the prettiest decimal. It's got a nice repeating pattern to it. I think it's 0.1666666. All right, so around 16.7%. Now let's do letter C. Find the probability of flipping a head and rolling an even number. All right, why don't you go ahead and do that? All right, I still find it easier to use this one than this one. I'm looking at finding the probability of flipping a head and rolling an even number, so I'm only going to be on these branches over here. Specifically, it would just be this one, and this one, right? Not these three anymore, so let me cross those out. So that's going to be 3/12, which reduces to 1/4. That does have a nice probability, 0.25 or 25%. Again, we could certainly do the decimal and percent in letter B. It's not as nice. All right. So tree diagrams, really, really simple. Take each one of the simple events, flipping a coin, throwing a die, whatever you have, right? Pick one of them, doesn't matter really which one, and lay out its possibilities. Then draw branches away from those possibilities and list all the possibilities of the next simple event. And if there was a third one, like we had in the last case with the 3 coins, then we draw branches from each of those and list out those possibilities. Let's look at a rather complicated one in our last exercise of the lesson. Exercise number 4. Kirk. Oh, Kirk. Kirk is taking a 4-question true-false quiz for which he has not studied. Oh, Kirk. He will guess on each of the 4 problems. Letter A, create a diagram showing all possible outcomes that Kirk could guess. Now, this is what's called a 4-stage experiment, and the tree diagram is going to get ugly. And the probability Kirk is going to get every question right on this quiz, i.e. this guy, is also going to be kind of ugly, all right? But it's a 4-stage, right? It's question 1, question 2, question 3, and question 4. So literally, on question 1, Kirk could guess a true or a false. And maybe I'll put this additional branch up here, but you don't absolutely have to, right? But, I could have guessed a true or a false on question 1. I'm just guessing at random. I'm just like flipping a coin and being like, all right, I'm going for false, right? But then, of course, for question 2, if I guessed a true on question 1, I could still guess a true or a false on question 2. And if I guessed false there, I could do a true-false there. Side note, I would love to have a giant piece of paper for these tree diagrams. So if you need to do your tree diagram on a piece of scrap paper, do it there. Never, ever hesitate to use more paper, large amounts of paper to do your math. Never let cramped space and stuff like that get in the way of your education. All right, anyway, little rant there. Let me move this a bit over here and this a bit over here, because I'm gonna get crowded here. You can probably already see it, right? By question number 3, by the time I get to a 3rd stage event, right, now I'm gonna have a true false that I could have gotten, a true false, a true false, and a true false, and that's only on the 3rd question. Can you imagine if it was a 10-question true false test? It'd be so ugly. And then finally on question 4, if I can even fit it, right, I could get true false, TF, etc. I don't think you need to hear me continue to say true false. Whoops, Maybe put the F up here. This is apparently a tree that's growing all over the place and upside down. It's one of the weird things about tree diagrams. They always look upside down for me. Anyway, so here they are. And again, you can really trace kind of what's going on. Like for instance, if I traced this path, let me circle. That'll be easier for you to see, right? What does that path represent? That path represents Kirk guessing false on the first question, true on the second question, false on the third question, and false on the fourth question, right? That's simply that path, right? I could guess true, 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 and true, right? I could do all of that. Now, let's take a look at letter B. If the correct sequence is true, true, false, true, then what is the probability that Kirk guesses all of them correctly? All right. Well, I'd like you to play around with this, and I'd like you to express the answer not only as a fraction, but also get a percent, because I think the percent really hammers home how unlikely it would be that I would get a perfect on this quiz, even though it's only 4 questions, and there's only 2 choices per question, true and false. So pause the video now. All right. Well, first thing I want to know is how many possibilities are there? Remember, I can count the terminal branches, or I could say, well, there's 2 choices on the first one, 2 choices on the second question, 2 choices on the third question, 2 choices on the fourth question. There would be 16 possibilities. 16 possible ways that the teacher could arrange the answers to work out on this true-false test. But there's only one way that you get them all right. And that would be if you went down this branch. Let me put them in squares so that I can distinguish them a little bit. Right? Now that's not 4 possibilities. I want to be very clear. A given path to the end represents one possibility, TTFT. So think about like if we were listing these in an organized way. We would have TTTT, TTTF, TTFT, etc., right? This is just 1 out of 16, and that's the probability, right? The probability is 1/16 that I would guess all of these right, and if we do that as a decimal and a percent, 1 divided by 16, right, is 0.0625, multiply that by 100, and we've got 6.25%. Wow. We have less, sorry, I shouldn't say we. I have less than a 10% chance on this true-false test of getting a perfect, of getting them all right if I'm guessing, right? And that's because there's 16 total ways I can guess, all shown in that tree diagram. All right. Let's wrap it up. So today we worked more with compound events, and probably the most important thing that we introduced was the idea of a tree diagram, right? A diagram that literally shows us, okay, here are the outcomes that could occur in the first part of our compound event. Then from each one of those branches, all the possibilities that could occur in the second part of our compound event. And from all of those branches, if we had a 3-stage event, all of those, then a 4-stage event, all of those, etc. The more stages that you have, of course, the more complicated your tree diagram would get to both draw and to analyze. So you probably won't have to deal with anything more than like a 4-stage event, because quite frankly, you saw with a 4-stage event, each stage only having 2 possibilities each, how complicated it can really get. All right. But we'll see tree diagrams here and there in our final few lessons in this particular unit. And of course, you'll see them a lot more as you move on to do probability in later courses. For now, I just want to thank you for joining me for another NGen Math 7 lesson by eMath Instruction. My name is Kirk Weiler, and until next time, keep thinking and keep solving problems.